three things to cover. One is what happens when you have indeterminate structures. So we will cover indeterminate structures. Okay. Next is we will cover how to, even in indeterminate structures, we will have two portions. One is flexibility method. We'll discuss this, what is flexibility method. And the other one is stiffness method. Then we slightly cover what happens when you have thermal strains. Third is stress concentration. Okay, with that, we will finish our part on axial members. Okay, so this is what we are going to learn today. Strain energy you have learned in the last class already. Please do few examples with strain energy for getting a hang of it. Okay, so these parts are covered, so we will not go through them. We will just go directly to our statically indeterminate problems. So what are statically indeterminate problems? So structural problems or machine element problems are of two kinds, as you all know. One is determinate problem, and we all know the definition: number of unknowns, unknown forces, you can say, is equal to number of equations. Okay, and the next is, second is indeterminate problems. Number of unknown forces is greater than number of equations. What we do in those cases? In those cases, we make use of extra unknowns, extra equations are obtained using compatibility conditions. Okay, which are generally geometric in nature. Geometric in nature. When I say geometric in nature, it means it comes from deformation relationships. Okay, it comes from the deformation constraints that we have on the structure. Now there are two ways of doing this. There are two ways of getting this compatibility condition, and we learn both the methods. Okay, you may not get in any book in details as it's going to be taught in this class today. If you want to have a proper understanding of flexibility and displacement, you have to follow a little bit older books like Mechanics of Materials by Gere and Timoshenko, or any Timoshenko books. That is what you have to follow. Okay, Gere and Timoshenko. You may not get it as clearly as there in Gere and Timoshenko, in Hibbeler, or in other books. Okay, so pay attention. Go back to your book, read it. The problems will be solved as it is, but they will not tell this is a stiffness method or this is a flexibility method. Okay, so when you read it, when you learn it, when you study it, please pay attention what method you are using, because finally you have to you have to at least expertise one of these methods. Okay, right. So we have discussed what is a statically indeterminate structure. We have discussed what we do in when we have a statically indeterminate structures. Okay, one small question. I have discussed two conditions here. One is when number of unknown forces is equal to number of equations. That is called determinant, and we can solve it using equilibrium conditions, right? The free body, you can draw a free body diagram and then put your equilibrium conditions into it, equilibrium equations into it, and then you will finally get the reaction forces or unknown forces. So in case of indeterminate structures where the number of unknown forces is greater than number of equations, you get the extra equations needed to solve the problem using compatibility conditions. Now the third thing is, what happens when your structural unknown forces are lesser than number of equations? What happens in that case? Can you please answer it on the chat? If you know it, what happens when you have number of equations available is more, whereas number of unknowns are less? Now, coming back to structurally indeterminate structures, we have two methods of solving. As I said, one is called flexibility method or force method, as the name suggests here, force method. The other one is stiffness method or displacement method. Okay, right? This is very important in the sense that for problems where you don't have many degrees of freedom, it will not be difficult for you to do it by hand. But when you have a lot of degrees of freedom, let's say you are working with tens of degrees of freedom, or maybe hundreds of degrees of freedom, or thousands of degrees of freedom. We are not going to hundreds and thousands because those cannot be solved by hand. Those mostly you will need ANSYS or other finite element softwares, or you have to write finite element codes to solve. Okay, but till a certain extent, maybe 10, 15, where you can do things possibly by hand and simple MATLAB calculations, you need to learn which method you are using, because when the degrees of freedom are large, like 10 or 12 or 15, I'm talking about large in the sense that much amount only, and you want to try it by hand, you have to form a matrix equation and you have to solve that matrix equation. Okay, generally matrix equation that is solved is K matrix, you get it, and your unknown degrees of freedom X is equal to your known force F. Okay, you solve it in this format. So therefore X is the degrees of freedom, X is K inverse F, where K is stiffness, right? So you get it in the matrix format. Okay, K is the stiffness, and this can be written as flexibility inverse. Remember that K inverse is flexibility matrix. So flexibility matrix into forces. So both methods are useful, but you need to know which method gives you an easy matrix, the matrix format, the elements of this matrix, these elements that will be there in the matrix. So if you have 10 degrees of freedom free, if there are 10 degrees of freedom in your system, then your matrix size will be 10 cross 10. Okay, K matrix size will be 10 cross 10. So you need to know which method gives you these elements of 10 cross 10 matrix easily. And that's how you have to use one of the method, either flexibility or stiffness, and that will come with your practice. As much as you practice, the easier it becomes any of the method that you use. Okay, right. So let's start with this. What is a flexibility method? A flexibility method, here the redundant variables we consider is the force. So whatever extra unknowns that are available, extra unknowns that are there, we consider all of them to be known force variables, and then in terms of that we solve the complete problem. It will be the equation. Okay, we'll get back to this. All right, so now the other one is the stiffness method, where displacements, okay, displacements becomes the primary variables which we assume is given, and then we solve the whole problems with the displacement being given, and then finally we put the constant equation to solve the whole equation of equilibrium. Okay, let's see how it is. Okay, let's take one problem here, the first problem. Now when I draw a problem like this, let's first take a slight thing here. Okay, I have a problem here, okay? You have a bar and you have a P force given here. Is this problem determinate or indeterminate? So there is A point here, B point here, and C point here. Unknown force. To RA, right? You want to find reaction at A possibly, because other points, it's no point of finding force. Reaction at A. And known equations, number of equations. Or let's okay, number of equation is 1. What is that? Summation of H or force H. I will write it as force H equal to 0, right? And that gives me RA plus P 0. How are you going to get this? You have to draw a free body diagram here, right? The free body diagram, if BD is going to be something like this. P force, and here it is RA. So in this case, I have given an opposite direction. Yeah, I have given an opposite direction. So if that side is positive, then it has to be RA plus P equal to 0, which gives me RA equal to P. So this is I have used only the equilibrium equation to solve this. Okay, so this is a determinate problem, right? So I can write it number of unknowns to 1. Number of equations equal to 1. Number of unknowns equal to 1. This makes this a determinate problem. Now I just extend this problem to a little bit more complicated condition. So let's say I have again the same boundary condition and I have the same rod here, but now I have other boundary condition here that this point is also fixed and then there is a P force here. Now in this case, what are your unknowns? Now if you see number of unknown forces, equal to 2. What are these unknown forces? Draw the free body diagram. P. So here it will be RA, here it will be RC, ABC, right? ABC, A, B, C, RC. So unknown forces are RA and RC. All right. Equations. Equal to only one equilibrium equation as earlier one if H equal to 0. Now can you solve this? So what we get is minus RA plus P plus RC equal to 0, right? Therefore we need 2 minus 1 equal to another one more equation to solve the problem. Right? Okay, now let's look at how we do it. Okay, let's look at the problem. So this is my problem. I have both methods here. One is flexibility method I have both the methods here, flexibility method and stiffness method. Okay, I'm not solving here, I'm just telling how to do it. Solutions are afterward. So let's look at flexibility method, how we do in flexibility. We said that flexibility method, the primary unknown will be your force, and you'll assume one of the force as a variable and solve the full thing given that force. So here the equilibrium equation that we have solved it. So this is the condition of the problem, right? This is the problem. So this is a bar which is fixed on the top and the bottom. Bottom is fixed at B and top A is fixed, right? So A and B are at this boundary. So my problem here is a little bit different. For example, here it should be B and this should be C. This is C, this is B, then this is B, right? This is B, this is B. And this also has to change to C and this change to B. Okay, then it will match whatever I have here. Right, so this is the bar, neglect the currently the weight of the bar. So you have connected at A and B. A and B are fixed at the top and at the bottom. And there is a P force acting at the point C. C may not be at the center, anywhere on the top side it is. The point of location of C from the top is L1 and from the bottom is L2. Okay, clear? Now, if I draw free body diagram as I've drawn earlier, if I draw free body diagram, it's going to look like this. So if I replace this boundary from here, I will get one force that is acting here, RA. And if I replace this boundary B from here, I'll get another force here, which is RB. So that constitutes its free body diagram and the P force acting here at C. Right. So the equilibrium equation, if I put the equilibrium equation, it's going to be RA upward positive. Here RB is also upward positive minus P equal to 0, right? So P comes on the other side, it becomes RA plus RB equal to P. That's my equation 1. And I need to find another equation to solve it. As I said, the number of unknowns here is 2, RA and RB. Number of equation is 1, right? So this is an indeterminate structure. And redundancy, number of indeterminacy or redundancy is 2 minus 1, 1. So I need one more equation to solve it. And that one more equation should come from the compatibility condition. So in flexibility method, we assume unknown force as the primary variable, right? Here the number of redundancies is 1, so we need to assume only one of the force to be known to me. So we assume RA to be the redundant variable. So let's assume that RA is available to you. So if RA is available to you, that means this boundary is not there. So I'm freeing one of the boundary. Remember that the number of indeterminacy is 1, and therefore I'm freeing one of the boundary. Okay, I'm repeating again, since number of redundancy is 1, I am freeing only one of the boundary along one direction. Okay, please note that the direction is important and the number is important. So I have removed this, and when I remove this, I have to put RA here because I cannot just remove boundary, I have to put the force that was there. So this part has been made free and there is a RA force that is acting here, and this is the boundary here. That is fixed. So this problem has been reduced to this problem. Now look at this problem. Look at this problem. If RA is given to you, what we are assuming right now, RA is given to me. So if RA is given to you, then this problem is a determinate problem. Right? P is known, RA is known, and there is only one boundary. Then you can always solve this B in terms of RA and P, right? So that's what is a flexibility method. We'll come back to flexibility method once we solve it, but how much it's different in a stiffness method. For a stiffness method, we said that the primary variable is supposed to be a deformation, a degree of freedom variable. Okay, it should be a degree of freedom. So the primary variable here is the deformation, and we assume that delta C is known to us. What is delta C? Delta C is deformation at C, right? The beam, if you the bar, if you see, will not move at A, neither it will move at B, but it will have some deformation at C because of the force given or before of the stresses and strain along the body. Let's say that I know delta of C here. Okay, assume that I know delta of C. So what will happen? I will take a free body diagram just above it, and I'll take a free body diagram just below the point C. Okay, take two sections at AA and B be just above and below the point C. If I take just above point C, then I don't have any force acting there. So this is my just above C. What will the force acting there? There should be RA on this side and RA on that side, right? P force is not yet acting because P force is acting from point C. Okay. Now I know the deformation here, the extra deformation that this point C has gone through is delta C, which is assumed. So I will know RA is EA by LA into delta C. This is from my last two classes, that delta C is PL by AE. So the force that is acting here is RA. So it's going to be RA into L by EA. So RA is going to be, since RA is unknown, is going to be EA by L into delta C. Okay. Similarly, the force that is acting on this part of the body is going to be RB, because there is RB acting here, and you have taken a free body diagram just above it, below it, right? Just below the point C. So P is not working yet. So this is called RB, and that has compressed by delta C. If this has elongated by delta C, this is compressed by delta C. And therefore, RB is going to be EA by LB into delta C. So both the forces now, RA and RB, are known in terms of delta C. So if I can find delta C, I'll find RA and RB. In this case, also, if I can find RA, I can find RB. Now, how are we going to find RA, or how are we going to find delta C? This is the question that we have, and we have to understand how to solve for RA. If I, in a flexibility method, if I can find RA, I can solve the problem. In a stiffness method, if I can find delta C, I can solve the problem. Now let's look at how to solve RA and RB. So let's go to flexibility method first. Now, I have divided this work into various steps, for us to easily understand. What we have done is we have removed the upper part, and then we have replaced it with a force RA. So assume the variable unknown for the force, right? So let us assume RA is available, or let us remove, let us don't write this, let us free the top boundary and replace it force RA, right? Okay, we will solve in terms of RA. What is the equilibrium equation? You know already the equilibrium equation. Equilibrium equation is going to be, RB. If I assume RB to be on this direction, then it's going to be RB plus RA minus P equal to 0. That's your equilibrium equation. Okay. Now, what we can do? We can do few things here. Now, look at this problem. There are two forces that are acting on this problem. One is RA, one is P. Okay. All right. Now, I can use superposition principle because this is a linear structure within its linear elastic limit. Therefore, I want to find deformation at A. What would be the deformation at A given B? B is fixed. So deformation at A is going to be, because of the RA, there will be a tension in the B member, and that tension is going to be RA into L1 by EA. Okay. How are we going to get this? For getting this, what we have to do? We have to take free body diagram and we have to find internal forces. Remember that what we have to do? We have to find internal forces. Okay. So if you do free body diagram, is there a space here? No space. Okay. FBD, right? So first section is AC. What we're going to get? We're going to get something like this. I'm drawing it horizontally. Okay. This is my A point. And then this is going to be RA, right? And that is up to L1 position, and then another free body diagram of the section BC taken from the bottom side. So what I'm going to get is RB, on the other side also RB. So internal force diagram is going to look like this. Going to look like this. So it is, let's say this is B and that's A. It's going to look like RB and then RA, something like that. Okay, it's going to look like this. And then if you want to see one thing, that P force is acting towards the bottom side, so RB is going to be negative. It's going to be compressive, right? Because it's pushing the material on this side, right? Compressive. So my diagram here is not correct. It has to be on the opposite direction. Okay, so here also the diagram has to be changed. RB, RA, positive, negative. Okay, so now how do we find the total deformation? The total deformation is if you remember that total deformation is given by the formula summation of Ni Li by Ae. Okay, what is my Ni here? So one portion has Ra, the other portion has Rb, right? And Rb is compressive, so that's going to be negative. So RaL1 by Ea minus RbL2 by Ea. So that's going to be your delta A at A given delta B at B0. Okay, so that's how you find it. Now, what do we have from the problem? From the problem, what do we have? From the problem, what we have is this is the compatibility condition. The compatibility condition now kicks in and it tells that delta A given B is 0. So this is fixed. That was also fixed in the actual problem, right? So in an actual problem, your whatever be your RA, your delta B is going to be 0. So that guy is going to be 0. And if you put that equal to 0, you have to put this to be equal to 0, right? Now, if I put that to be equal to 0, that becomes my second equation. So this is my first equation, which is my equilibrium equation. And the compatibility condition gives another equation, which is this, supposed to be equal to 0. Now you have two equations, you can solve them. So you can write RA in terms of RB, which is written here. RA in terms of RB, it is L2 by L1. Please note this ratio. These ratios are very important. As I was discussing in the last class, that most of the load sharing happens in terms of the stiffness ratios. So you can see here, since EA is constant, it is actually a stiffness ratio. Okay, so RA and RB is like this, and then you can plug it back into equation 1, where RB L2 by L1 plus RB equal to P, which gives me RB as P L1 by E, P into L1 by L1 plus L2. Similarly, RA will be P into L2 by L1 plus L2, which is L. So you can see it's like the sharing of the load has happened in terms of ratios of L. It's not actually ratios of L, it's actually ratios of the stiffness of upper part and the lower part, remember. Now, see, EA being constant on both sides, the EA here and EA here cancels. Okay. So please note these ratios. These ratios will keep coming in center of material, and you have to keep it in mind, because many times you will see there are a lot of members that are coming and joining, okay, in a section. Again, in that case, if there is a single load, the load will be shared in terms of their ratio of their stiffnesses. So that is always going to be an easy check for you when you solve a problem. Okay, before I go to okay, then you can determine the stresses once you know the loads, and you can determine the strains also once you know the load. Okay, this is, I will leave it to you to do it, but you can do that, right? Once now my problem is solved, right? I know my RA that is given by this. I know my RB, which is given by this. Okay, since RA and RB are known, you know what is the stress that is acting here, and you know what is the internal force that is acting here, and you can solve for stress. You know what is the internal force that is acting here, and you can solve for that stress also and strain also. Right? So do that yourself. We looked into the flexibility method, and we have seen that it's not very difficult to solve a flexibility method given the problem that I've shown you. Okay. Now let's look at stiffness method, how easy it's going to be. The problem that I've given you, if you assume that problem with a spring analogy, it will be like there is a fixity here, there is a fixity there, and in between the fixity there is a force P acting, and between the force P and the fixity there are two different kinds of members, not different kind of, two different sections of the member are there, right? So we can assume that this body, uh, it is fixed here, it is fixed here, and there is a point P. So this point P is trying to pull this kind of materials here and push this materials here, right? So it's going to move like this point C. So point C is moving like this. So I can assume this part to be acting as a spring, and this part also is acting as a spring. So I can represent that as two springs with different stiffness because the portions are different. So the stiffnesses are going to be different, and a P force acting there. So this is K2, which is near your B point. So probably this is B, and this is your A. Okay, right? And that gives you actually how much your movement of P going to be. How much your point here, the point C is going to move will depend on the relative stiffness of K1 and K2, right? And that's what I am showing here. Okay, let's solve it. We said in the problem before that what we will do is we'll assume that there is a small deformation at C, right? That is delta C, and it is the free variable in our stiffness case, right? And for this delta C to happen, RA has to be EA by LA delta C, and for this delta C to happen, RB has to be EA by LB delta C, right? We have understood from the free body diagrams. So if you take a free body diagram only for the upper section, just above C, point C, and then the forces will be RA and RB. With this force in the section, the deformation is going to be RA LA by ES. EA is going to be delta C, and therefore delta C is going to be this. Similarly, for this portion, we can write this. Okay. Now, coming back to your stiffness method, this is what we got. RA is equal to EA by LA delta C, and RB equal to EA by LB delta C from the earlier equations. Now, what is your equilibrium equation? Your equilibrium equation is RA plus RB equal to P. Now we can put this back here. RA is EA by LA delta C, RB is EA by LB delta C. Now, this is one equation I have, and how many unknowns do I have? I have only one unknown, delta C. Because RA is represented with respect to delta C, RB is also represented with respect to delta C. Right? So when you solve this, you get delta C to be PA LA LB by EAL. Just solve it, right? So EA goes common, so EA PA by EA it becomes, LA is there, LB is there, so it becomes LA into LB on the top side, sorry, LA into LB in the bottom side, and the top LB plus LA. So that is what is there. LB plus LA is L, so EA by EA into L in the bottom denominator and P into LB into LA in the top. So you can solve that, right? Now you can use delta C, put back to this equation to determine your RA and RB. So RA is going to be EA LA by delta C. So you multiply with this, EA cancels, right? LA cancels, it becomes PV into LB by L, and RB becomes P into LA by L. The same thing that we got solving these equations. All right. So the internal forces are now known, so stresses and strains can be determined. All right. Is that clear? Any question that you have? We have another problem here. The simpler version of this problem is given in your assignment, and we have solved also in the last class with only two members, two bars, right? So we had only this bar and this bar. We did not have this bar. Okay, now we have that bar also. So Is it a determinate problem or an indeterminate problem? Let us first look at that. Okay. So how many members we have? We have 1, 2, 3 members. So if I take a free body diagram here, cut this here, I will get FA, FB, and FC as 3 forces. And this is my point P acting here. So I have to solve for 3 unknown forces. And how many equations we have? Since this is a 2D problem, I have 2 equations. One is summation of H equal to 0, summation of V equal to 0. I cannot use the moment equation because all the members are coming to a point. Right? So if I take a moment about this point, this will be 0, this will be 0. Moment due to this force 0, this force 0, all the forces will be 0. So moment equation cannot be taken. Plus, this is a truss problem. Okay? It's not a bending problem. So system is therefore indeterminate. So I have 3 unknowns and I have 2 equations. The system becomes an indeterminate problem. What I can do, I can use my horizontal balance equation and I can say that FA and FC are equal, right? Because it's a symmetric problem, which is very evident. If the material properties of these two are same, then FA and FC are going to be same. We cannot get this from the symmetry. We can get this from the symmetry as well. Summation of V. What does summation of V gives me? Summation of V gives me 2FA cos beta plus FB equal to 0. So there is FA here, FC here. Both of them will have a component on this direction, right? That is FA cos beta into 2 is for the 2 forces plus FB equal to 0. Equal to P force. Yeah, total force is P. Now I have to find a redundant. No, so I have now 2 unknowns, FA and FB, and I have only 1 equation. Right? I have already consumed my H equation, so that is no more useful. H equilibrium, that is no more useful. So I have only 1 equilibrium equation, that is this one, 2FA into cos beta plus FP equal to P. And I have 2 unknowns, FA and FB. So now I have to either go for flexibility method or go for stiffness method and find how to solve a problem, solve this order. So number of redundancies, 3 minus 2 is 1. So we need to consider at least 1 force known. So let us consider FB to be redundant variable. Okay. Now, when I said that I will, last time also we did that when I say that FB is redundant, is we will free the degree of freedom there, free the boundary condition there, right? We'll put a degree of freedom. So what we do is we remove this bar. FB is due to that bar, right? So we remove that bar, and if you remove that bar, you get a force here, right? And we put a force here, FP. I cannot just simply remove that bar. So I have to replace that bar with a force FP. I have given a force FP. Now you see, you have 2 members, right? And you have 1 P force acting here and 1 FB force acting there. So eventually it is P minus FB force acting downward. So this problem you have solved on your in your assignment. So this problem is solvable because this is a 2-member force, right? With a P minus FB force acting here. So it's a determinate problem now. But in terms of FB, right? Not in terms of anything else. So you can solve that. Now what do we have? A geometric condition we have. Now geometrical conditions tells that delta BD, where is BD? This is B, this is D. Delta BD is equal to be FLBD by AE, right? Because of the force FB, and delta at DE is going to be F P minus FBL into 2A. Okay, let me explain here a little bit more. So now this condition I can draw in 2 problems. One is like this. B FB, right? Plus no. If that is that side, this will be FB here. This is B, this is C, this is A, this is D. Clear? So this problem is now divided into 2 problems, right? So deformation at this point D is due to this problem plus this problem. Okay. Now let's look at it. So you can see that FB direction here and FP direction here are taken care, so that balance becomes 0. So please note that. Now delta BD in this member is going to be due to FB, and that is going to be FB LBD by AE, right? This is LBD. Okay, B and D. So that's going to be FB LBD by AE. Now for this problem, the delta is going to be, we have solved that problem already in the last classes. The delta is going to be P minus FB into L by 2 AE cos cube beta. This has come from, check from your assignment. Or last class. Want me to go and show? I think I have that here somewhere. Yeah, you see. So this is the problem now, where instead of P, you have P minus FB, right? So this will be, this is the solution, P minus FB into H. In place of H, you will have, this is my H, right? Instead of H, you have LB by 2 A cos beta, something, cos cube beta, whatever is there, right? All those things will come here. So that's thing. Okay. Now for compatibility, what is going to happen? This point is fixed, right? These 2 points are fixed, both are D point. And therefore this rod cannot have a separate deformation, and this rod cannot have a separate deformation. Both should have same vertical deformation. Both should have same vertical deformation to make sure this point remains the same, right? So that's my compatibility condition. And that gives delta D should be equal to delta BD. Therefore, you can equate these two forces. Once you equate these two forces, what is your unknown? Your unknown is only FB. And you have only one equation here. So once you solve it, you get the value for your FBD. And once you know FBD, you can solve for FAD or FCD. Because one of the force known means other force can be obtained easily. So once you know this, you can solve for this. You can use it in equilibrium equation and solve the problem, right? So use equilibrium equation. Okay, right? One check you can do is, what you can do is you can put beta to be 0. So if beta becomes 0, all the 3 member bar comes here, right? So this becomes a 3 bar together vertically. So each bar will take 1/3 of the load. So you can put that here and see whether it matches or not. With that, I'll stop here.